Hello everyone! Today's experiment we're going to try to find out the wattage of the sun. We're going to use information from Blackbody radiation. We have three equations that are going to help us figure out the wattage of the sun, like how much power the sun is radiating, how far away the sun is, how bright the sun is, what the temperature of the sun is, and how big is the sun. That's pretty cool, or pretty hot. So the way we're going to set this up is we're going to use these three equations. The first equation says that your peak wavelength, or the maximum wavelength that you emit, is equal to this constant, 2.9 times 10 minus 3, over your temperature in Kelvin. So there's like a conversion between what wavelength of light is produced and what temperature in Kelvin would produce that wavelength of light. Next one is to calculate power. Once again, we have another constant times the surface area of the object times temperature to the fourth power. The last one is intensity. The intensity is like how bright something is, or how warm something is, or how hot something is at a certain distance away. The farther away you are from something, the lower the intensity, because intensity goes down by a square. So the equation for intensity is power, how much power is radiated, whether it's light power, heat power, sound power, whatever it is, whatever kind of power it is. Power over 4 pi r squared. 4 pi r squared is the surface area of a sphere. And you can think about why that works is because let's say I had like a campfire, for example. A campfire. Alright, if I'm right next to the campfire, it's pretty intense. There's a lot of power there. There's a lot of heat, a lot of light, really bright, a lot of heat going off. But the farther away I move from that campfire, it's less and less hot, and it's less and less bright. So that's the same thing with any object. The power is going to diminish as you go farther away, because basically there's energy radiating out in every single direction, and it's going to make a circle. And in a three-dimensional space, it actually makes a sphere. And so really, if I were an object at this point, the amount of energy that gets to me every second is going to be determined by, well, how much energy is produced here and how far away I am, based on the surface area of that sphere. So how far away I am, surface area of a sphere is 4 pi r squared. That's where the equation comes from. So we're going to use a combination of these three equations to figure out everything we can about the sun, even though it's really far away. So to do this experiment, we're actually going to start with this bottom equation. And what I have here is a couple wax bars. So it's a wax bar with aluminum foil and another wax bar. And the cool thing is, when light hits the wax bar, it illuminates it. It makes it glow a little bit. And then it reflects off this middle surface of aluminum, and it makes that side glow. So it can't get to our wax bar. So I turn this up. You can see there's lights above me, so it's hitting this top wax bar, so it makes it glow, but the bottom wax bar is in the shadow, so it makes it dimmer. If I turn this upside down, now you can see, hey, now it's still the top one that's doing that. What I want to do is I'm going to place this wax bar, I'm going to have this light bulb here. Now this light bulb I know is the wattage. I know the wattage is 200 watts because I measured it. So it's a 200 watt light bulb. So I'm going to hook this light bulb up, and I'm going to place this light bulb a certain distance away from the wax bars. It's going to make one wax bar glow. It's going to make it light up. The sun is going to be on the other side. It's going to be in the sky. So I'm going to have the sun really far away, and it's going to light up the other wax bar. And I'm going to position this wax bar so that both sides are evenly, are basically the same brightness, the same intensity at that distance. Now obviously this is going to be much closer to the wax bars than the sun is, but we're going to use this relationship of, hey, at some distance away, this light bulb is going to appear just as bright as the sun. Obviously, we're going to have to be much closer to the light bulb than the sun, but we're going to use that relationship of intensity is power over 4 pi r squared to figure out how far away the sun is, and also how much power the sun has. So let's get cracking. So here you can see I have the lamp set up. It's on the ground. It's a 200 watt lamp, and I have it positioned directly in relation to the sun. The sun is shining right on it. So both objects, the sun and the lamp, can shine on this wax bar. So here's my wax bar here. I'm going to try to position the wax bar so that the lamp is on one side and the sun is on the other side, and both sides are equally bright. Now you notice here, I adjust the distance, and right about there they're equally bright. This side and that side are equally bright. They're not the same color because they're emitting different wavelengths of light, but they are equally bright. So now I'm going to measure the distance from the center of the lamp to the center of the wax bar and get that rough estimate there. And if you can see, my estimate is about 11 centimeters to the center of the wax bar. So there's my scenario. One side I had a 200 watt light bulb, the other side I had the sun. Obviously much not on the scale at all, but so you could fit it on this board here. And this side of the wax bar was the same brightness as this side. Now this side was yellow, this side was mostly white, because the sun and the lamp are emitting different wavelengths of light. But I was looking for intensity, not color. We're going to talk about color later. Now, I labeled the distance from the center of the sun to the center of this wax bar as D1, that's distance 1, and I labeled this as D2. And what we found is the wax bar is showing us that the intensity of light getting to this wax bar is the same intensity of light as getting this bar, because they're equally bright. What we want to do is we want to use this information to figure out what is the power of the sun. So we'll start with that. I'm actually going to use this intensity equation here. So what I have here is the intensity of the sun is equal to the intensity of the lamp at that distance. So now I'll do a little substitution here. I'm going to actually write down the power. I'm going to replace this intensity with the equation for intensity. So the power of the sun divided by 4 pi r squared of the sun equals the power of the lamp divided by 4 pi r squared of the lamp. Well, turns out that I can simplify this a little bit because I have something over 4 pi, something over 4 pi. So the 4 pi's actually cancel out. I don't need the 4 pi's because they cancel out on both sides. So I can get rid of those bad boys. And then what is this r? The r is the distance from the sun, because this is, you can imagine the sun is radiating light in every direction, so it makes a sphere. So the r is the radius of that sphere, but the radius is just the distance away. I measured that distance, or I can use that distance. So this r is just d1, and this r is just d2, because once again, this is radiating light in all directions, and so the radius is the center of the lamp to that distance away. This is d2. So let's rewrite this a little bit. So power of the sun divided by d1 squared. Now, the distance to the sun is actually a known value. There's lots of experiments that prove this. There's geometry that works. There's something called parallax that works. There's high clever optics that works. And we'll learn about those types of techniques to figure out the distance to the sun later. But just know that it's a given value. It's 1 astronomical unit. 1 AU. AU! That's the distance to the sun. Now, what is that in meters? Well, this is 93 million miles, or 150 million kilometers, which converts to 1.5 times 10 to the 11th meters. That's a known value. That's in your IB formula packet under a couple of different spots. It's under astrophysics. It's also under your conversion page. So 1.5 times 10 to the 11th. And then once again, it's squared, so that's my value, that's squared. Okay, so we have D1, and it equals the power of the lamp, which we have is 200. 200 watts. And we did measure that D2. Now, I estimated the best I can. It was somewhere between 10 centimeters and 11 centimeters. I want to round up to 11 centimeters because I want to measure from the filament of the lamp to the middle of the bar. So 11 centimeters. This is where the biggest uncertainty is going to come in right there. 0.11 meters. And that's squared once again. So now we have our equation. And the only thing I don't know in this equation is the power of the sun. So to get the power of the sun, what I have to do is just multiply this over on the other side, so the power of the sun ends up being 200 times 1.5 times 10 to the 11th squared divided by 0.11 squared. We're going to get a really big number. And the units will be watts because we have square meters here, those cancel out. This is watts, so the units are going to be watts. And we just crunch the numbers to figure out the power of the sun. All right, bada bing, bada boom. I did my magical calculation here, and I calculated it to be 3.72 times 10 to the 26 watts. That's huge. I can't even fathom that number. It's just ridiculously big. Now, the accepted value for the power of the sun is actually not that far off from that. It's 3.86 times 10 to the 26 watts. Now, when I say not that far off, that's like 14 million watts off that we were. But compared to as far as percentage-wise, it's pretty close. We're pretty close as, maybe like 5% off or less than that. So We found the power of the sun. Very good. The next step is what we're going to do is we're trying to figure out the temperature of the sun. Now, we can use this equation to find the surface temperature of the sun, not the temperature of the core, but the surface temperature of the sun. And we can actually do the same thing for our light filament too. What the temperature of that filament is using that same equation based on the wavelength of light produced. We're going to do that next. All right. Now the sun, just like any other thing that radiates heat, which is almost everything, makes a graph that looks like this, where the y-axis of the graph is like the amount of light or intensity of light of each different type of color, and then the x-axis is the wavelength of light. Now, so light has different wavelengths based on what color it is, and here's all the different colors of light. Some of them we can see, some of them we can't. Here's the different colors. There's gamma rays, which are very, 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 very small and very, 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 very harmful. Gamma rays. There's X-rays. We can't see X-rays. We can use X-ray imaging to convert X-rays to light, visible light, but we'll talk about that later. There's X-rays. Those are also very harmful for us. There's ultraviolet light, which is also very harmful. Now, the cool thing about X-rays and gamma rays is that a lot of our magnetic field from the Earth and our atmosphere can deflect those away. So those don't get through. But the ultraviolet light does get through. So that's the harmful ones, because the first three here, gamma rays, X-rays, and ultraviolet light, are harmful to our bodies as organisms. So ultraviolet light can get through. Violet gets through. But you can see there's not a lot of ultraviolet light, but it's enough to be harmful. Violet light gets through. It's not a lot, but there is violet light getting through. Blue, green, yellow, orange, red, all those colors actually are being emitted from the light, and then from the sun. And then there's infrared, which we can't see. It's outside of visible spectrum. And then there's radio waves. Radio light waves, that's also a type of light waves. The sun's emitting all of those, and all of those are getting through with the exception of the first two, and some of the radio waves. But anyway, all the rest of them get through. So basically, when you put all the lights together, the entire spectrum appears white to us. It appears as white light. And that's why the sun appears like white. But some people often draw the sun as yellow, and that makes sense because it emits more yellow light than any of the other lights. Now, it appears white because it's emitting all of them, but if you were to look through a very high, precise polarizer, it's going to appear yellow. And so the sun is actually emitting a little bit more yellow light than the rest of them. So the peak wavelength is yellow light, and yellow light has about a wavelength of 500 nanometers, about. So we're going to use that for our peak wavelength. So we're going to use the equation lambda max, which is like the peak wavelength, equals the maximum wavelength, 2.9 times 10 to the minus 3 over temperature. We're going to rearrange this for temperature, so temperature, multiply this on both sides, so temperature equals 2.9 times 10 to the minus 3 over the peak wavelength. Now, nanometers means a billionth of a meter, so it's going to be 500 times 10 to the minus 9 meters. So when I crunch those numbers in my calculator, I can find the temperature of the surface of the sun. So 2.9 times 10 to the minus 3 equals, divide that by 500 times 10 to the minus 9. Make sure you put parentheses around this number and parentheses around this number. And you get a value of 5,800 degrees Kelvin. 5800 Kelvin. That is the temperature of the surface of the sun. Not the core of the sun, that's much hotter, but the surface of the sun has the temperature of 5,800 Kelvin. That's pretty hot. Finally, we're going to use this middle equation here to figure out the size of the sun, basically the surface area of the sun. So I'm going to rewrite this equation here. This thing right here is called Stefan-Boltzmann's constant. It's a constant. It's in your formula packet. The constant has a value of 5.67 times 10 to the minus 8th. And basically it's just a constant to make the units work out. It's a conversion factor. Multiply that by the area of the sun. Now remember, the sun is a sphere. And the surface area of a sphere can be found by 4 pi r squared. We just talked about that. Except this time, the r is not the distance away from the sun. It's actually the radius of the sun, because we want to figure out the size of the actual sun itself. So I'm going to put that in. I'm going to put in 4 pi r squared, because then I want to know the radius of the sun. And now I know the temperature. That's 5,800. And that's raised to the 4th power. That temperature is raised to the 4th power. 5,800. Now, in our first step, we found the power of the sun. The power of the sun that we calculated was 3.72 times 10 to the 26 watts. And look at that. We have every piece of information here to figure out the radius of the sun. Once you find the radius of the sun, it's basically telling you, oh, the distance from there, the center of the sun to the outside of the sun. You double that, and you can find the diameter of the sun. All right, so I crunched the numbers here. Based off this equation, based off the measurements that I made, the radius of the sun ended up being 6.79 times 10 to the 8th meters. If I double that, I can find the diameter, or how wide the sun is, which is 1.36 times 10 to the 9th meters, which is another way of saying over 1 billion meters wide. 1.36 billion meters wide. Wow. Or 1 million kilometers wide. Now, Earth's radius, just as a reference, is 6 million meters, basically. So if you divide this by the Earth's radius, you basically fit over 100 Earths along the edge of the sun. So basically, if this is the sun, I can fit over 100 of them, over 100 Earths, side by side by side by side, touching from one end of the sun to the other end of the sun. That's pretty big. And if you have done any traveling, you know how far, imagine how long it takes you to go from one end of the Earth to the other end of the Earth. Well, multiply that by 106, and there's your sun. So the sun's a pretty astronomical object. Now, here's a final closing thoughts on an experiment like this. There is a lot of uncertainty with it. It's not perfect. We're doing a lot of estimations, but we did get pretty close to accepted values. But one thing to note is when you deal with equations with really, really big numbers like this, or really small numbers like this conversion vector, make sure you use parentheses around everything. Every single number should have parentheses around it. So this should have parentheses. When you put it in a calculator, don't type it in as one thing. Put parentheses around every single step. Break it into small pieces, because I actually had to calculate this like 2 or 3 times before I got the right value. I'm like, what's going on? Well, what I ended up doing is I forgot to square root the radius at the end, because I calculated everything and I got the radius squared equals something. I was like, oh, wait a second. Make sure you square root. Make sure you solve. One way to do it is to solve for the variable first. If you have this equation written out, solve for the variable that you want first, and then start crunching the numbers. But I guarantee you, put parentheses around these things, especially with scientific notation. Your calculator doesn't know how to do it. So make sure you put parentheses around it because you know how to do it. So guide your calculator. Tell the calculator what you want it to do, and it'll do what you ask it to. So that's my closing thoughts. Hopefully you guys can use the information that I gave you or your own experimental data to find the power of the sun and how big the sun is. So good luck with that.